Great. And as a quick reminder, I'll drop the link to the live stream page in the Zoom chat because there's also a chat on the YouTube page. So we just want to keep an eye on both for Q&A. So you are live.
Sure. Shall I begin?
Yes, please.
Yeah. Okay. Well, thanks very much for the invitation to the organizers. So it's an interesting group for me and my colleague Alexandru to be here. As we understand it, it's a mixture of people who are interested in telecommunications and Hyperledger. So yeah, really interesting to meet everyone here, and we want to make this as kind of interactive as possible. So feel free just to shout out any questions during the talk, and I might even pose some questions to you guys. So this is the agenda. So I'm just going to give you a quick overview of who nChain are, and then there'll be two parts to the main talk. So firstly, my colleague Alexandru will talk about some research we've done. It's ongoing research, so there's plenty of opportunity here for you guys to give us feedback, whether you think this is a good idea, whether you have any suggestions, etc. And we'd be really interested to hear that. And then I'm going to end with just something a bit more fun, which will be a general kind of discussion about what I'm calling high performance public blockchains, because I'm not sure how aware you guys are of the kind of current state of play in that particular area. So yeah, I'll just start with who are nChain. So we're a company with over 250 employees based in the UK, Switzerland, and Slovenia. So I'm based in the UK, I'm in London. My colleague Alexandru is in Switzerland, and then we have some people in Slovenia as well. And we have 17 scientific researchers, and me and Alex are two members of that team. And we started out really as a research and development first company, which is a bit unusual. And the research we're doing back then is really trying to lay the foundations, the kind of scientific foundations of blockchain and how we might use that in at a large scale and for enterprises. We then introduced a software engineering department in 2016. And one very interesting piece of software they produce is the node software for a blockchain called Bitcoin Satoshi Vision, BSV, which I'll talk more about later. And it's the highest performing public node software out there. And by that, I mean, whichever metric you prefer, like transaction volume, block size, throughput, etc. Then we introduced what we call a business service team in 2019, trying to look at the market, seeing where the kind of inventions we have might best fit. And we're gradually transitioning into a product company. So starting to build out on a lot of this expertise, which is a really exciting place to be right now. Anyway, that's a bit of an overview of nChain, and I'll now hand over to Alexandru. So hopefully he can control my screen.
I think so. Let's see. Yeah, I can. Okay, awesome. Right, so let's run a bit through the motivation for this research project, why we want to use the blockchain together with peer-to-peer networks. So it was shown in the academic literature that if you have a lack of economic incentives, peer-to-peer networks have difficulty scaling. You might have some kind of community incentives whereby you share files, but that already is applicable if the peer-to-peer networks are at large scale, so they wouldn't face this problem anyway. So then if we do add economic incentives, it was shown, for example, I think it was first shown maybe in 2012 in a research paper by Microsoft that introducing this will add C-bill attacks, because network nodes are then incentivized to create a lot of fake identities throughout the network and gather as many economic rewards as possible. And the third motivation for this this research is a question that arises, for example, during COVID times, and during COVID times we saw a lot of network load on peer-to-peer networks, and there's a natural question on how or who should pay for this network load. Right, so let's cover a bit of background in order to set up the work. Let's look at first at Gnutella, which is quite a famous peer-to-peer network. It was the first decentralized network of its kind, and it was introduced in 2000. And funnily enough, its name comes from Nutella and GNU, the legend says at least. And it was or is still a file sharing network that I think is still active. So the request of Gnutella is the architecture of Gnutella is rather simple, and it's a request response type of network interaction where we can request data through the network. And the queries are sent to our peers, and our peers forward the query to their peers. Once a node is identified that holds the required data, there's a response sent through the network back to us, notifying us that the data has been found, containing also the information of this peer, so that we can establish a direct TCP or UDP connection with the node, and we receive the data. Now on to Onion protocol, which we will turn on its head, but let's cover the basis of this first. It was first introduced as for anonymous communication, and it's still being used for that. And it was introduced in the mid-90s to protect US intelligence communication. It's currently used as part of the Tor network, if you used it until now. And it's let's look at its architecture, a brief and very succinct overview of how it works. Let's say we have 3 nodes in the network, and we want N1 to relay data securely to N3, passing N2 such that N2 has no idea of what it's being, what it receives and what it sends to N3. So if you're aware of some cryptographic concepts, N1 and N2 first perform a Diffie-Hellman key exchange, whereby they establish a shared secret between them. This will be a cryptographic key. And then N1 can establish another shared secret with N3 through N2. So N2 will relay the public key of N1 to N3. N3 can create the shared secret, and it can send the notification that it has created the shared secret, and it sends its own public key. So at this stage we finalize the Diffie-Hellman key exchanges between all these nodes, and we can securely relay the data. So we encrypt the data in 2 layers using the first shared secret between N1 and N2, and the second shared secret between N1 and N3. Once N1 sends this encryption of the data to N2, N2 can decrypt the first layer, but it still doesn't know the data, right? So then it just sends the encrypted data to N3, and N3 can then decrypt the result and do whatever it wants with that data. Right, this is a very simplified example. The Onion protocol contains several other details, but this is a brief overview of how it works for 3 nodes. Right, so now that we covered the basis, we can look at how we can enable data transfers using Gnutella and Onion protocol, while crucially enabling the economic incentives I mentioned, and we will use blockchain for that. Right, so let's cover Gnutella, and we will have a Gnutella on chain. So in this framework, the protocol runs as follows. N1 will send a request for a data in a double hash. And it will send to its peers also a transaction payment with some conditions we will cover a bit later. And N1 too, so the one of the peers will forward the request to its peers, N1 to 1 and N1 to 2. Now, I want to pause at this stage and emphasize the fact that the transaction payment, this is mined on the blockchain. So when N1 sends the hashed request, it will send the hashed request via TCP/IP, for example, to N11, and then mine the transaction payment with the necessary conditions on a blockchain of its choice. And the other peers do the same thing. Right, so now we identified the green node, and the green node has the data. So then the green node lets the whole network know that it has the data by publishing H0 so the inner hash of the request. And once it has made this broadcast, letting everybody know that it has this data through H0 N1 and N1 and the green node can start a connection where N1 to 1 will send the data and it receives some payment from N1, and the payment will again be done through the blockchain using a transaction or a sequence of transactions. So crucially, none of the other nodes will know what H0 is unless they know the data. And for example, the green node can have an association between a database associating possible requests with its data. Right, so what are these conditions I was talking about? And because this is a crucial part of using the blockchain, having just normal payments can be enabled through I don't know, any other kind of digital payments. Maybe you want to use some PayPal APIs or something like that. But with blockchain, we can establish some conditions with this payment. Peers will receive payment only if the preimage of the first hash, so only when H0 is broadcast. They don't receive money for a 3, because if they did, then they can just run away. There's a question, is the data payload on the blockchain? No, the data payload doesn't have to be on the blockchain. I think that will blow up transaction sizes quite a bit. And that's not necessary. I think so. N1, well, the peers between N1 and the green node can communicate in such a way that, let's say, N1 will start receiving chunks of the data, and for each chunk, it will send back a payment. This is basically creating a payment channel between N1 and the green node. Right, okay. So then the second spending condition is the fact that the broadcast of H0 will, the peers will receive payment only if H0 is broadcast within a certain time frame. So that's crucial for having a very responsive peer-to-peer network. And for this, we do need a very high throughput blockchain that can mine transactions rapidly so that this answer time is relevant. Right. Another thing I want to emphasize here is the fact that the hashes don't have to be cryptographic, or they shouldn't be cryptographic, because if they are, then it makes it very hard for this thing to work. If anyone makes a typo in its request, then you know, the data will never be found. So we suggest using what's called locality sensitive hashes, whereby if the hash has a typo, then that's still fine. Either the hash will still be the same, or it will just change slightly. So that makes it a bit more practical. Now the peers, the blue nodes in this case, that's not a problem. Even if they want to brute force it and find this pre-image H0 of R of the request, they won't have time to, because if the answer time, if the time frame N1 wants the answer within it's like 1 or 2 seconds, then they won't have time to brute force and retrieve the request or H0 of R. So that's one observation to how we can make this work. Now, before I move on and introduce how we can use the Onion protocol, and this is for the people in telecom working on, let's say, 5G antennas and so on, and maybe looking at the internet infrastructure. Imagine the red node and the green node are 5G antennas, and the blue nodes are data centers. So in this case, what does it mean for N1 to receive payment, to receive the data directly from the green node? They communicating directly will mean bypassing the internet infrastructure or having an additional infrastructure. So that's not feasible in a way. So the only way N1 can receive in this kind of infrastructure the data from the green node will have to be from the blue node N1 too. So this is why we introduced the Onion protocol, or we use the Onion protocol to enable the data transfer. And we switch focus on the Onion protocol. The Onion protocol, as I said, was developed with an anonymity goal in mind, but we switch focus from that to payments. So what do I mean by that? If the red node, if all the communication, for example, is done in clear, right? What can happen is that N1 can, for example, sniff on the communication between the blue node and the green node, receive the data, and never have to pay the blue node ever. Right. Then you can say, okay, maybe we want to encrypt the data with, let's say, some TLS, and N1 can't sniff. But then if N1 pays for the whole for the whole chain of transaction payments, as it should, because let's say it requests a movie and it has to pay the cost for N1 to relay the data, then if we just use some TLS encryption, secure communication protocol, then N1 can just decrypt and also benefit from the data. So that's not good either. And lastly, a third reason for why we use Onion is, let's say, okay, so let's say we make N1, we make the whole channel of communication use N1's private key to encrypt the whole data. Sorry, the N1's public key to encrypt all the data. But then again, we are back to this first case where N1 can sniff on any segment of communication receive the data for free. Right, so that's those are the three reasons why we need the Onion protocol. And I guess when you deploy it, you can use an Onion protocol maybe with 2 layers. You don't have to encrypt for all the hops. You just need an outer layer encrypting with the keys of the current hop, and then the inner layer encrypting with the public key of N1, and that would be enough. Right. So remarks, as I said, we can combine the request and data propagation protocols. And the pros are, we use the same peer-to-peer infrastructure to propagate the data. We can control answer to requests using spending conditions. But the cons obviously are, if we don't have a very high throughput infrastructure, then if we use Onion in the way I explained, then this might lead to lower propagation times. Right. Are there any questions until now? Okay, then I can move on. And I can tie in the story because until now we talked about payments, but we didn't talk about how we can keep the any of the peer-to-peer nodes honest. So for this, we will record the network structure on chain. Right, so as I said, if we do this, if we record the network structure on chain, then any dishonest node can be provably identified because many blockchains are public. And peers can have joining fees and specializations. This will be mostly like a byproduct of recording the network structure on chain. So how can we ensure that nodes or peers are honest in the network? Peers can monitor each other's activity on the public blockchain, and N1 will always maybe have questions like, did N12 forward my request? And N12 can have questions like, did I receive enough payment for forwarding the request? And all these questions can be solved if we use a public blockchain where we store the structure of the peer-to-peer network, so that N1 can look at the transaction N12 mined and see if it mined transactions for its peers, and similarly N12 can compare how much it received with how much N11 received. So how do we do this? Let's say, how do we record the peer-to-peer network structure? When N1 wants to join the network, it can establish a connection, handshake, TCP, IP connection. And then for this connection, it will send a transaction payment with some spending conditions. So what are the spending conditions? N1 pays N2 for connecting. The second is N1 will deposit some additional funds. In order to redeem the funds, every time N1 disconnects from N2, it will have to signal this, and then it will recover the money. So in this way, we can keep an integrity of the network structure on chain, because otherwise N1 could have just disconnected from the network and we would never know it. So in this way, we offer an incentive for N1 to be honest and signal when it disconnects. But still, if it doesn't, N2 is entitled to receive the funds. And then N1 can specify or update its network. Let's say you have some, you want some nodes to signal to the network that maybe they are good for file sharing, or they want to be used some kind of like a DNS type of node. You can end up modularizing a bit the peer-to-peer network, depending on the roles. Right, so finally, I want to talk about Sybil attacks. And the Sybil attacks, if they are executed, they can bloat up data request payments by, for example, tricking a node into thinking it has more peers than it actually has. Bloat up data propagation payments, for example, in the Onion protocol, it can trick a node to think so that it thinks that it has the data was received through many hops instead of just one, for example. And this can be prevented if we have a trusted third party, whereby nodes are issued some certificates on chain, or through web of some kind of web of trust. And I think we are achieving a web of trust by having this fairness type of protocol between nodes, where nodes can monitor their peers and they are trying to make sure everybody's being honest. Right. Okay, so other questions? Right, so I don't know for a Lightning Network, the inner details of the Lightning Network, but we are very much focused in this architecture on providing the right incentives. And I think by using a very high performant blockchain, such as BSV, you can handle all the, you can handle a lot of transactions directly on chain, basically. Yeah, I don't know if that answers the question, but. How do you avoid? Right. Should we continue with the presentation, or should I answer more questions on?
Oh, please, yeah, continue with the presentation. So this is Alex's last slide. So after this, I'll completely change gear. So I think it's best to ask any questions you want to ask to Alex right now.
Right. Okay.
Plenty of time. I won't take long for my bit.
Right. So how do you avoid legitimate looking nodes from colluding to bloat or otherwise attack it? So I guess this goes down again with the issuance of certificate of nodes on chain. And I think once, let's put it this way, once you detect the nodes detect an attack, or you see fees bloating up, you can punish your peers by never requesting, by never sending requests through those nodes, right? And what will happen is that those nodes will never receive payment again. I think this is more, it ends up like a very natural economic system, whereby if fees are bloated up so much that nodes don't have any incentives to pay, basically. Right. Yes. Okay, cool. So then, if there are not other questions, Owen, you can take it away.
Sure. Okay. 1 second. Okay. I hope everyone can still see the screen. Okay. Thanks, Alex. So I think Alex gave a really interesting use case for a blockchain that could allow for high transaction throughput at a very low cost. And that's why we could record all of this data, such as the network topology and requests. Someone asked about the Lightning Network. So to me, if you're not familiar, that is a layer 2 payment solution on top of BTC. And my understanding is it's more geared towards payments and then settling those payments on quite a complex payment channel on chain. I don't think it can deal with recording data immutably in terms of requests, etc. So I'll talk a little bit more about the type of blockchains that the construction Alex has presented might be able to handle that type of idea. So firstly, I want people to just shout out at this point. So can you give me any examples of public blockchains that you're aware of, or you're a fan of, or you've worked with, just so we're all on the same page? And I won't move on until I hear at least 1 or 2 suggestions.
Ethereum.
Yep, Ethereum for sure. Characterized by its ability to have smart contracts on chain and this notion of a global state. Very popular one. Mm-hmm. We mentioned BTC, so I won't give you that one. Any others that people have heard of?
Solana and Cardano.
Yeah, Solana and Cardano. Yep, for sure. Okay, thank you whoever shouted out, and that was you, Brian. So I've just taken a cut of some of the most popular public blockchains that I just took from this website the day before this talk. So you'll see this is cut according to transaction volume. I don't actually think they have Solana here, so it's not completely representative, but it gives you some idea of how many transactions are going on these blockchains. So Bitcoin BTC with the highest market cap in blue, you'll see at the top there. So just a kind of smaller but not insignificant fraction of transactions. Ripple has the most, and Ethereum close second. The one that Alexandra and I are particularly interested in is called Bitcoin SV, which is in this kind of light green color, and you'll see that represented there in the top left. Okay, so it's just some examples of public blockchains. And what are the problems facing public blockchains, in your opinion, or challenges we have to overcome?
I would say it's proof of work versus proof of stake versus proof of history, which is more efficient based on the use cases.
Yeah, so it's interesting. So proof of work certainly has a high energy usage. Proof of stake doesn't require any link to hardware, I would say. And proof of history is the part of a hybrid consensus that Solana uses, I think. So yeah, I suppose the word efficiency there is an interesting one to pick up on, because what do we mean by that? You know, if we use a lot of energy and therefore, you know, at the moment CO2 to maintain something like BTC, which is quite a low volume blockchain and primarily used for payments and things like that, perhaps that's not a very efficient use of energy. But if we have a very scalable blockchain where you know, a lot of people, businesses in the world can use it as a kind of immutable record of history, then that is potentially a much more efficient use of that energy. And perhaps we also don't need to use as much. So I'll touch on that in the next slide. Any others? Any other challenges?
Well, there's the transaction latency, transaction throughput.
Yep.
Scale.
Yeah, exactly. So transaction throughput is low, meaning it can't do many transactions per second. Latency, I take that to mean when I send a transaction, I have to wait until I can be sure that it's actually confirmed on the network. So yeah, both those things are challenges. Okay, thank you. So I won't ask for any more there, but here are some that I wrote down. So they're quite similar to what you just suggested. So high fees is another one, particularly on public blockchains. Low transaction volume, slow confirmation times, so related to latency. Sometimes they just have network outages because the technology is too new, particularly in the more recently proposed blockchains. One that I'd like to touch on is a long-term economic sustainability. What is the outlook for these blockchains over the next 10, 20, 30 years? And there also can be issues with how they've sold the tokens before the blockchain was launched, particularly in the case of Ripple. And funny enough, a lot of these issues were not present in the original design of Bitcoin. I'm not going to go into all of them right now, but I'd love to talk to more of you about that after the talk if you want. But for now, I'm just going to focus our discussion on, before we begin, is a little quiz. So I was at a conference a couple of weeks ago called CoinGeek, and in it, they talked about the first blockchain. And my question to you is, which year was this deployed? And another related question is, why is this chap holding a newspaper? Okay, someone in the chat said 1998. Interesting.
Are they holding a newspaper for proof of time?
Okay, yeah, could be. In what sense?
Well, like when you have a hostage, right, and you hold up the next day's New York Times, show proof of life, right?
Yeah, that's a terrifying but scary analogy, fair analogy, I think. Okay, so I mean, one obvious answer would be 2009 when Bitcoin was released. It is earlier than that. We have 1998. Does anyone think it's even earlier? Okay, well, I'll put you out of your misery. So let's just play this clip and see what this guy has to say. By the way, his name is Stuart Haber, and he deployed him and his colleague Scott Stornetta deployed the first blockchain. And here's his little explanation. So I hope you can hear the sound on this, and someone shout out if you can't.
Sound. So what that is a so Scott and I deployed our system first in commercially in 1995. How did we achieve? We built a blockchain, but we needed to achieve worldwide consensus on occasional ones of these hash values. Okay. How did we do that? In 1995. Mm-hmm. Actually, we did this already in 1991 when it was still experimental code at Belcore. We built a new Merkle tree once a week out of the block by block hash values, right, and put the root of the Merkle tree in a classified ad in the national edition of the Sunday New York Times. And so this is an ad in the Sunday New York Times from when was that, Ian? 2 or 3 years ago, walking through Times Square. And
I'm thinking it was like 2016.
Yeah, it sounds about right, yeah. And
why would you put it in the New York Times?
Excuse me?
Why would you put this in the New York Times?
The point is that, well, here, I've got a little show and tell.
Because it's still happening, right?
This is the New York Times from literally.
Yes.
I could have brought yesterday's. Today's Monday.
September 5th,
oh, there
2021.
You go. That's the New York Times. That's this one. And if you, I have to say this, the lead story from about a month ago in the New York Times was this delicious headline.
Oh, yes.
Which reminds me of the headline that was in the Genesis block of Bitcoin. Let me read it. Officials worry as crypto boom invades banking. That's a frightening prospect, isn't it?
Yes,
But
frightening.
if you follow if you go to the inside page, right there is a surety hash value, a hash value of surety that depends on every bit of the registration requests received by surety servers in the week before September 5th. And because of the chaining, depends on every bit of every request received by the servers since we launched it in October 1991.
Okay, yeah, thanks for watching that. I mean, I was absolutely fascinated when I listened to this panel. So Haber and Stornetta, they were referenced in the Bitcoin white paper, I think more than one reference actually. And they deployed this blockchain in 1995, and it's still going to this day. And I don't know if you caught exactly what he was saying, but the way they did that was they would have a server, the surety server, that would receive requests in a week, and they would collect those in a Merkle tree, just like in Bitcoin. So that's away from going from a very large number of data entries to a very small Merkle root. And they published that in this lost and found column, or notices and lost and found in the New York Times. And the reason they did this was because the New York Times was widely distributed, across the world in libraries, etc. And they thought, well, this is a mechanism that's very difficult to cheat. If it appeared here, then in order to remove that proof, you would have to either remove or edit all of these newspapers. And moreover, it was really a blockchain. So the next Merkle proof also included the hash of the previous Merkle root. So it was chained together. And the key point here, I think, is the public nature of this process. So no proof of work, incidentally. And I'll send the link to this talk after in a follow-up to the email to this meeting. But even at that time, Stornetta, the moderator, asked him, did you believe your system could scale? And he said, I had no concerns at all. And the reason was they were using this Merkle tree structure that allowed them to very, very efficiently scale their system to as many data items as they needed. And their blockchain, it didn't contain a notion of payments. It didn't solve the double spend problem, which is what Bitcoin really did. But it was an immutable timestamp server of documents. And that was the problem they were trying to solve. It's like, if you have a digitally signed document, how do I know that signature wasn't just put on yesterday? How do I know it really was put on there 10 years ago? And they're very effective in that. So that's going back right to a proto blockchain before Bitcoin. Then Bitcoin came along in 2009. Well, I mean, the paper was released in 2008 and it was first deployed in 2009. And there are different approaches along the way. And I want to focus on two of them. So one is what is called Bitcoin Satoshi Vision. And the other is Bitcoin Core BTC, which is the one you'll be more familiar with, which has the highest market cap. And they were the same blockchain until 2017, when there was a difference of opinion in where the protocol should go. There are a few differences, but one of the main ones was in block size. So in BTC, block size was restricted to 1 megabyte. And as far as I can tell, this was done for more of an ideological reason, so that everyone who wanted to could run a node. So if you keep the block sizes small, that's certainly possible. Whereas the BSV camp thought, no, this should be market driven, and the block sizes should be as large as is needed for the people who want to use it. So let's see where these two blockchains have ended up now. So the graph on the left, which I took from this website again just yesterday, the yellow line is BTC, and this is average block sizes per day. And you can see BTC is just 1 megabyte the whole time. It will always max that out because there's more demand than can be filled by that block. And in BSV, you can see it did start out as quite lower than this 1 megabyte, because it was a chain that people were just starting to use. But then it grew pretty quickly to average similar block size to BTC. And now eventually, more recently, we're averaging over 100 megabyte blocks. That's every 10 minutes, over 100 megabyte block size needs to be propagated around the network. And the fees are different as well. So in BTC, the fees are rather large. I think the average is $1 or $2 per transaction. And in BSV, they're very low. And that's this statistic on the right, that it's nearly 7,000 times more expensive to transact on BTC. And that's in cost per byte. So per byte of data, that's how much more expensive it is to transact on BTC. So if we're characterizing these two, BTC has small blocks and very high fees, whereas BSV has big blocks and very low fees. And it's called Satoshi Vision because it was most aligned with the original vision of Satoshi through the white paper, the original implementation, and through the correspondence that he did before he left the project. And there was a recent report, like an independent study, trying to analyze which blockchain was most closely aligned with the original vision, and that the conclusion was BSV. Okay, so this might be all well and good, you would say, that it's not such a great statement to say, well, obviously, if the fees are lower, then it's easier to have a higher transaction volume. But the crucial part is the relationship. So suppose I reduce my fees by a factor of 10, but it attracts 100 times more users to the system sending transactions, then overall, I'm actually going to be an economic advantage. And this has a big implication for the economy of the mining market. So the graph on the left has just changed, although it looks quite similar. And what you're seeing is the fee to block subsidy ratio of the network. So this is how much revenue a block generates for a miner, how much is made up of the transaction fee. So in BTC, you can see it's around 10%, dropped down recently to more like 1%. And BSV is going in the other direction. So it started out quite low, which related that low transaction volume. And as the transaction volume has increased, fees have remained low, but the percent of the block reward is much higher. So now we're getting to BSV nearly 10%. And why is this significant? Does anyone know?
I'm trying to parse the graph a bit about the mining award versus the transaction fee.
Mm-hmm.
Can you explain again where they converge? One is getting lower mining rewards and higher transaction fees?
Yeah, I think so. I should have changed this before I presented it, but I think they shouldn't say the word reward here. I think that should be block subsidy. So the subsidy is the fixed amount of Bitcoin that you get for mining a block. And
the 6.5.
Yeah. Actually, it is fair because there's an implicit subsidy there. Yeah, this is the total reward. How much of that, which is a combination of subsidy and total transaction fees. And this is what percentage of that is transaction fees.
Well, based on that, I think the challenge in the future for BTC is as the halving events occur, right? There's going to be less mining awards. So you need the transaction fees, but you don't want them to skyrocket, obviously, right?
Yeah, exactly that, Brian. So it's the halving of the block subsidy. So this is the subsidy is the fixed number of Bitcoins you get when you find a block. And it started out with 50 Bitcoins per block in 2009 and halves on average every 4 years. So went down to 25, 12.25, etc. It's now 6.25. In 2024, so only a few years away, it will halve again to 3.175, and it will keep reducing by half. And if you're going to fix your block size, I mean, no matter what it is, you don't have much wiggle room. If you're a miner and you want to recover the losses you're making every 4 years, then you are going to have to raise the fees. So that could be a big problem facing BTC in the future. What do you do about that? I don't know. But BSV has this other dimension, which is transaction volume. So as long as you keep increasing your transaction volume, you can make up the shortfall. And this graph doesn't quite do it justice because, oh, sorry, the previous graph from transaction volume, because that was the average per day. But in BSV, some of the blocks are very small, some are very, very large. And actually a very significant event happened a couple of months ago, the first time ever on any public blockchain. There was a 2 gigabyte block on BSV, and there was more revenue in the transaction fee than there was in the block subsidy. So we're getting to a point where it's becoming more and more of a stable economic system long term. And so eventually when the block subsidy reduces to 0, we're making so much transaction fee by that point, it doesn't matter. So this is the long-term economic sustainability of both blockchains. And, you know, it's something that's not talked about a lot, but it's very, very important. And we believe fundamentally the correct approach is to have bigger blocks, smaller fee, and a higher transaction volume. Okay, so how do we get there? And this slide is called Terranode, because Terranode is a project at nChain, which is the next kind of upgrade to the node software. And exactly as the name suggests, the goal is to get to blocks that are 1 terabyte in size. And how do you do that? So we're getting close to the limit of scaling up our node software, which means you can, if you keep upgrading your computer's hardware, then you can process more transactions, you have more bandwidth and more memory. But they'll get to a point where you just can't do it on one machine anymore. So instead, your node will be a cluster, and you just keep adding cluster nodes to deal with the higher demand. And they're actually, they've prototyped this and tested it. They're very confident that they can get close to 100% scale factor. And as you people might know, being telecoms minded, one of the tricky things will be bandwidth. So this is a very interesting research question if you're in the telecoms industry. How do we get 1 terabyte size blocks propagating around the network? What does that mean for transactions? So I just did some quick calculations, and that should be 1 million transactions a second need to be sent around the network. And it's kind of different from other types of data transfer in the sense that a transaction needs to be registered at every node. So it's like the propagation of a state update for that particular UTXO. So very interesting research question. I'm for sure we're going to have to use the expertise from the telecoms industry. If anyone's interested in finding out more about that, then please just have a chat with me or Alex afterwards. Okay, that was really it for my part of the talk. So thanks for listening and for shouting out. And I just thought I'd end with this slide, which doesn't even make sense grammatically. But like, what if we're a group of people from Hyperledger, Bitcoin SV, and the telecommunication industry? What do we have to say to each other? And a part of me thinks actually Hyperledger is more, there's more ways that Hyperledger and BSV can complement each other than other public blockchains, because my understanding of Hyperledger is it's very effective in creating private distributed ledger networks, and perhaps Bitcoin SV is the complement to that. So just like in the original blockchain, they wanted to publish a hash commitment of their data once a week in a newspaper, perhaps Hyperledger in a private blockchain context wants to have some of that on a more transparent, immutable ledger. Perhaps it's something like they want the access control structure or identity management on a public ledger, but actually the majority of the transactions will be on their private system. Could be something like that. And yeah, it's the same with the telecommunications network, as Alexandra, I think, discussed well about how do you deal with incentives. And I read the other day, like a very funny story that Squid Game, which is the show that I'm sure everyone has watched, it became so popular that there were real bandwidth issues, and it wasn't clear who should be paying for that, which element of the infrastructure should be footing the bill for all of this extra bandwidth. So yeah, I guess that is a real problem, right? If I'm reading about it in the newspaper, and perhaps that's something a public blockchain might have a contribution to. Okay, and lastly, thanks for listening, and here's some references to things I've talked about, and I'll share this after the talk if you want to learn any more about anything we've talked about. So yeah, that's it from my talk. I'll look at the chat to see if there are any questions?
So thank you, Owen, for the talk, and it's Nima here.
Oh, hi, Nima.
Yeah. So thanks. It was a very interesting talk. Also, the use case that we had with the peer-to-peer networks. There was lots of questions, interesting questions as well. Regarding the final Hyperledger walking into a bar with Bitcoin SV, or really the idea of Hyperledger and initially was to provide that consortium blockchain space as an alternative to public blockchains, right? But then as it progressed, there are now lots of projects within the Hyperledger umbrella that are trying to actually kind of make a bridge between Hyperledger and lots of other public blockchains. You have kind of a separate consortium blockchain that could also be connected to any public blockchain in a controlled manner, of course. So it's not really Hyperledger is not really just a dedicated private blockchain. So first of all, there are lots of sub projects in Hyperledger.
Well, that's something that we're quite interested in, is can you create a permissioned environment within a public blockchain? And, you know, quite a silly analogy, but one that I think is maybe fair, or is how I think about it. Like in the early days of the internet, you had different organizations had their own intranet, right? And that worked very well because they had their own controlled environment. But over time, people realized it really does work best if we use one protocol, the internet, TCP/IP protocol. And if we're careful enough, we can migrate our private networks into the cloud and then get the best of both worlds. And I wonder if a similar process we might think about that as happening here.
Well, I mean, I think that the analogy does make some sense, but at the end of the day, all of these, like when you want to deploy Hyperledger network, you are more likely to use actually the internet infrastructure, right? Because you have to make sure that your nodes are going to be able to talk to each other, right? And you're not going to deploy your own optical infrastructure to connect the Hyperledger nodes, right? So you are kind of going over the internet, right? So yeah, I mean, and then similar to what we have now with the enterprise networks on the internet, they use their own protocols, they use VPNs, and those are the tools they use to kind of create their own island within the whole internet that we have. So I think that's kind of a better analogy to kind of trying to see where Hyperledger and its ecosystem could actually kind of be relevant in the world of public blockchains, right? But there's no denying that there's market for both of these, let's say, and there are lots of good use cases for both of these types of blockchains, right? So for that peer-to-peer network that that we just saw, of course, like a consortium blockchain wouldn't really be kind of ideal for that use case, right? Because you want everyone to be able to join and host kind of peers and in that network. But then you have also lots of other use cases where just you can't even imagine having that use case in a public blockchain, right? So yeah, I mean, the thing that I really appreciate here is that we have really similar concerns here, because usually when you go to the public blockchain kind of world, people don't have the concerns that we have, especially in Telecom SIG group. We have really big concerns around the transaction throughput and the latency, because we can't just wait 10 minutes for a transaction to go through, right? So we really need kind of live information, real time kind of transactions and so on. So I think that's something that we can definitely work on.
Could I tell you, now you brought that up, just how that works in Bitcoin SV? So as I'm sure a lot of you are aware, in BTC, the block confirmation times are 10 minutes. But they also have another feature, which is equally challenging, which is called replace by fee. So if I send a transaction to a BTC node, and then a few minutes later, I send a transaction spending the same output, but for a higher fee, then they will prefer the second transaction because they will get a higher fee. Now, in Bitcoin SV, by the way, that wasn't in the original design of Bitcoin. In the white paper, it says nodes should accept the first seen transaction. And it's related to scaling as well, because if you're a node that is dealing with 1 million transactions a second, the logic of having to replace some of those transactions and all the knock-on effects downstream is so costly that it's not even worth your while to do it. So what they did in Terranode is, the rule is, if it's a first seen transaction, we will record it and we pledge to do that. And you can lean on our reputation as miners to have assurance that that transaction is the one that will be published in a block. And that's an instant thing. So as long as I send my transaction to the majority of nodes and they tell me it was the first seen transaction, then I can be assured that it will be mined into a block. So we call that zero confirmation transactions. And that's why in BSV you can send money instantly. So again, a lot of these problems at scale kind of iron themselves out. Sorry to interrupt you, Nima.
Yeah, no. That's and we have similar. Let's say in Hyperledger Fabric, there's mechanisms that allow you to limit the number of verifiers and limit the number of endorsers that you need for a transaction to go through, right? And that kind of helps with the transaction throughput and latency and so on. But at the end of the day, we usually, in consortium blockchains and private blockchains, we don't really have kind of that concept of prioritizing transactions based on the fees, because usually we don't really have transaction fees. We're assuming that there are some partners that are partners in business that are kind of deploying this consortium blockchain, and they don't really need to worry about kind of transaction fees, and they actually don't want to. And even if you go to larger scale use cases of consortium blockchains such as IoT, that's also quite a bit kind of difficult to imagine asking kind of IoT devices to pay transaction fees or charge transaction fees to transmit sensor data to their network. And imagine that the only thing that we are trying to do with blockchain here for IoT is to kind of make sure that it's more secure, the connectivity, right? But then if you try to go to an operator or to a vendor and say, we're going to charge you a fee to be able to transmit your data from your sensors to your network, that's just not going to work. Usually they're not a big fan of paying fees. So and that doesn't really, I mean, you can go to them and say, I'm going to reduce the transaction latency by 500% if you pay certain amount of transaction fee, but that's just not really. They prefer to put in lots of more resources for their, let's say, blockchain nodes, the central kind of the kind of edge, let's say, Hyperledger blockchain nodes, rather than kind of paying third-party verifiers to actually verify the transactions. So that's really, I'm trying to really, at the same time, trying to find similar kind of paths here. Or
well, I think it's converging on the same idea that if you want real utility, which is high transaction volume and low latency, and I put it another way, for utility, you want very low fees and you want your transaction to, so you're in a situation where there are 0 fees. And the question is, how do you deal with double spends? And your solution was you just accept the first one you've seen. And that's it. And that's very advantageous from a utility perspective, because it means I'm not going to worry that in 10 minutes time, after I've already sent another 1 million transactions, the first one will change. So we're talking the same language there. And I think the only difference really is the fee very, very low, or is it 0? And that's the difference between a consortium model, I guess, and a public blockchain. And they have different features, like you say. I say the public blockchain is interesting if we can get to a long-term economically stable model, then we can have high confidence that that blockchain will survive forever. Whereas a consortium, you have the advantage of 0 fees, but I suppose it will survive as long as the consortium survives. It is quite a naive way I might look at it, but there's the trade-off. And also privacy, etc., that you mentioned.
Yeah, I mean, definitely there are ways to solve the privacy concern even, okay? But then I don't see any telecom operator kind of making their entire network depend on a transaction fee. And even if it's very, very low now, it's going to fluctuate with the price of a coin. Right? So, I mean, network operators want to be able to predict their costs years ahead, right? So they're not going to build in a fee into their system, even if it's very, very low at the moment.
Yeah,
that has the potential of growing, I don't know, 10,000% in the next 10 years, right? That's just, it makes it very unsustainable for
so why a process that is currently fee free would you ever introduce a fee for? I think that's a very fair argument, and I wouldn't contradict that. I'd say there might be some circumstances, which is not every single transaction, but it might be more like registering nodes to begin with and how you manage the topology of the network. That might be something you're prepared to pay a small fee for that to be quite transparent. And I would also think of the other aspect to this, which is not necessarily what BSV can do for the telecoms industry, but what the telecoms industry can do for BSV. Because if adoption continues to increase, maybe BSV will be the new Squid Game, right? Where there's a very interesting challenge there to manage who is paying for that and how can we make it more efficient. And even with, high volume data streaming, you can introduce payment channels where the only on-chain transaction is the final settlement, and that you can do using Nakamoto payment channels. So that there you're getting into a situation of pay per second of video rather than a subscription to Netflix, and maybe that can help manage that bandwidth problem.
Yeah, I mean, it is interesting, and one of the reasons that I actually was very interested to invite you guys for the talk was that in the Hyperledger telecom SIG, we have really focused on use cases of blockchain for telecom. But when I saw your use case with the kind of peer-to-peer networks and how they can support, let's say, kind of a blockchain kind of, or how blockchain can support peer-to-peer networks and kind of add some value there. It was interesting for me because that's something that we can also move towards. So yeah, I think we have to, if there are no more questions, let's just close it here. But it was a very interesting talk again. Thank you for the talk, and we would be very interested to have you and all of the participants that are now on the call joining our bi-weekly calls. It's always at the same time as now. We have if you go to the chat, we have the mailing list, so you can join the mailing list, and there's also the link to the wiki. We would be more than happy to continue this conversation in our bi-weekly meetings. Thanks again.
My pleasure. What I'll do right now is, if I can, I've pasted the references to the chat if anyone wants to look up some of the things we talked about just then. And thanks again for inviting us. It was a really stimulating discussion, and thanks for your input.
Great. Thank you very much, Owen.
Thank you. Thanks.
Thanks, Anne Sarah.
Thank
Thanks.
you.
Bye-bye.
Yes. Bye.